Let us start this lecture with a thought process by great scientist C.V. Raman, who says, "I feel it is unnatural and immoral to try to teach science to children in a foreign language. They will know facts, but they will miss the spirit." I really salute great scientist, Nobel laureate in physics C.V. Raman of having this observation, which is found to be correct, as most of our children are learning science in foreign language, that is English, and whatever he had predicted, it is coming true. So, it is a great loss to the intellectual abilities of our children, and we must correct it, and for that we will have to work hard and change the mindset of the people. So, let us now recall what we learnt in the last lecture. Here we started discussion on basically various materials that is being used for wall and close out and also coatings. Of course, some of these materials which are used are proprietary in nature. However, we looked at various kinds and just to have a feel for it. Later on, we moved into the other types of the cooling system that are being developed for cooling of rocket engine. And of course, we had a very good discussion on film cooling. Keep in mind that film cooling is one of them, and a question might be coming to your mind like, what will be the amount of coolant will be used in film cooling? Generally around 5 to 10% of the fuel or the propellant are being used. Well, and of course, there will be a loss of specific impulse due to the use of coolant in the film cooling, but one has to also take care of the integrity of the structure being subjected to high pressure and temperature. So, one has to minimize the amount of mass flow rate passing through the holes of the film cooling holes, and in order to reduce it further, people have devised the transpiration cooling, and transpiration cooling is the most efficient cooling one can think of as among all, because it uses a very less amount of the coolant, and it is also known as sweat cooling. Unfortunately, the materials which are porous in nature that can withstand high temperature and pressure are not available, and that can be manufactured easily. That is why it is not being used, as I told earlier, that it is being used nowadays for the cooling of injector head in case of cryogenic engine. Also, we looked at how we can maximize the heat utilization. For that, we use the regenerative cooling, and regenerative cooling is generally used in case of rocket engine. Later on, we also discuss about ablative coolings, in which the diamond or the copper or material which get eroded minimally, such that its temperature will be remaining constant at the or ablative points of the material. And beside this, we also discuss very briefly about heat sink method of cooling the rocket nozzle, particularly in case of the solid propellant rocket engine. Both the ablative cooling and the heat sink methods are employed for cooling the throat area of solid propellant rocket engine, because we do not have coolant. And keep in mind that oxygen free copper is being used as a heat sink material because of its having good thermal capacity and also the conductivities, or thermal diffusivity. So, today we will be looking at how to analyze these cooling systems and how to design by using certain expression and making the process to be very simple. Let us look at that today. As I had discussed earlier, that all three modes of heat transfer will be taking place during the combustion process and also heat transfer. And for design of cooling system, we need to consider all three modes of heat transfer, and those are the conduction, convection and radiation. Let us consider a diagram which is shown here. In this case, I have taken a cross sectional view of a combustor where you are having the cooling ports. These are cooling ports. It can be square shape, it can be other shapes, and it is having different aspect ratios that we had seen earlier. Now, this is the side in which the hot gases will be passing through. This is your hot side, because hot gases will be passing through this, and outside is your cold side or ambient temperature. And this is your outer wall, and this is hot side gas wall, you can say this one. And when these hot gases are moving at a high velocity and a high pressure, there will be heat transfer from this hot gas to the inner side of hot side gas wall of the combustor or the nozzle. There will be heat transfer due to convection. Between the boundary layer and wall interface, there will be of course the conduction, that is molecular conductions of heat transfer will be taking place, and in the wall itself there will be basically heat conduction. If you look at convection and also the radiation from combustion gases, which will be taking place simultaneously inside the combustion chamber and also inside the nozzle. As the propellant, either it can be solid or it can be liquid, but it may contains the particulates of both solid or the droplets. Therefore, that will be radiating the heat being at very high temperature, the wall. So, also the wall will be re-radiating to this. So, and flow will be turbulent in nature and it will be complex. And beside this, as I told that there will be heat conduction, the wall, and beside this the coolant will be moving at certain velocity across this one, right. This is your coolant velocity Vc, and this is your Vg gas velocity, and as a result the heat which will be passing due to the conductions through this wall, and that will be carried away, and it can be reutilized being a regenerative cooling system. And beside this there will be heat conduction, as I told these are conduction within the wall, and this is the wall, the metal wall, and this portion also will be heat being transferred to that. And if you look at this, all three modes of heat transfer will be taking place. As a result, that all these three modes of heat transfer occur simultaneously in the typical rocket engine combustion chamber and also in the nozzle. Hence, it can be considered as a conjugate heat transfer problem. That means, all these equation has to solve, as I told earlier, that the flow will be turbulent in nature. They will have to consider also the complex flow structures. There might be two phase flows, not only two phase, rather sometimes three phase flow will be taking place. So, therefore, it is very complex to analyze, and flow will be three dimensional in nature. However, for simplification and to carry out some kind of design analysis, we can consider the flow to be very simple and one dimensional in nature. And keep in mind, in actual combustor and the nozzle, the flow will be basically unsteady in nature to some extent. However, for our analysis, we will be considering the flow to be steady, and for that we are considering one dimensional flow, and this is your wall, and this can be possible if you look at, like, if it is the curvature of the combustion chamber and the nozzle is quite high, we can consider this wall to be one dimensional conduction, and having a wall thickness delta, and keep in mind, in that port the coolant is flowing through a certain velocity, and this is your coolant temperature T c. W c is the wall temperature on the coolant side, and there will be, of course, the heat conduction in this through this wall of the either combustion chamber or the nozzle. And the hot gas, we are considering that it is coming at a very high velocity. This is your V g, and which of course, there will be a boundary layer, because the wall is there on this, and it is also coming with a temperature, that is T T g. T T g is your total gas temperature. This is your total gas temperature, and T g is your static gas temperature, and we are assuming that it is dropping down because of heat transfer which will be taking place. If you look at the heat transfer due to the convection which will be passing through is G, and there might be also the heat transfer due to radiation, heat flux due to radiation which will be passing through that. That means, both the convective heat transfer and radiative heat transfer which will be taking place in this hot gas region, and it has to pass through the wall and under steady state condition. So, by considering one dimensional steady flow, which may not be true for our analysis to have a simple treatment, we can consider that the heat transfer flux can be determined as, that is due to the convection S dot G. This is H G is equal to H G T W A minus T W H. Keep in mind that this is your hot wall temperature, and T W A is your adiabatic wall temperature. That means, if this wall no heat being transferred, That means, there is no coolant, no heat being transferred, it is insulated properly. This wall, if you look at, this is insulated properly, insulation such that H dot total is equal to 0. Then this temperature will be, wall will be attaining at adiabatic wall temperature, and this is the condition of adiabatic wall. That means, heat transfer through the wall will be 0, and Hg is your convective heat transfer coefficient. Of course, if I know this TWH, TWA and Hg, I can find out what will be the amount of heat being transferred per unit area of the wall. So, this unit will be basically watt per meter square. This is the heat flux, that is your heat flux H dot G due to convection. So, however, if I know how much heat is coming and if I know the heat transfer convective heat transfer coefficient, then I can find out what will be W h, because W a I can calculate very easily, being it is adiabatic in nature. This heat transfer coefficient has to be evaluated. We will see how we will use, because for that the complete analysis has to be done, and including the conjugate heat transfer. So, let us look at now the same thing what we are considering, one dimensional steady heat transfer problems, and as I told that there will be heat transfer convection from the hot gas to the wall, and through the wall there will be conduction. This is only heat conduction. Along with this thickness of the wall, this is your wall, and this is of course will be convection, and in the hot side there will be radiation as well, apart from the convective heat transfer in the hot gas. So, by considering one dimensional heat transfer, the heat flux through the wall due to heat conduction is determined as H dot W, heat flux due to conduction, is nothing but your H dot W, and that we are saying that it is nothing but minus K W. K W is your thermal conductivity of the wall, and dt by dx, and this one has to obtain basically from the very rigorous analysis what will be the gradient, but we are considering that this will be linear in nature, and that K W T W H minus T W C divided by delta L, and as we are considering it to be a one dimensional, therefore, we can very easily. However, in real situation at least it will be two dimensional or three dimensional nature. And T W H outside wall temperature, as I told earlier, T W C is the cold side wall temperature, this is your T W C and this is your T W H, and delta L your wall thickness. And the heat flux due to hot gas site convection, heat convection, as we had already done, is nothing but your H dot double dash G is equal to H G and T W A minus T W H. And I have already explained about this, and H G is the hot gas convective coefficient, and similarly there will be convection which is going on the coolant. The coolant also will be carrying the heat whichever is coming through the wall due to heat conduction, and that we can evaluate, and heat flux due to the heat convection in the coolant passage will be basically this is your H double dash C and S double dash C is equal to S C into T W C minus T C, and T W C is the coolant side wall temperature as I told, and T C is the coolant temperature. This is basically the coolant temperature. Now, we will have to look at heat flux due to radiation, and that is nothing but your H dot double dash R is equal to epsilon G and sigma T Z 4, and sigma G is your emissivity of the gas, and which is quite difficult to evaluate, but however, we can take a constant value for our calculation. And sigma is your Stephan-Boltzmann constant, and which is a standard one, and this is H double dash R is equal to epsilon G sigma T Z 4, and heat flux due to radiation is proportional to the T G power to the 4, which is a very this thing. And beside this, there is a form factor which we have not considered, just to make it simple, and you can evaluate by this. And by considering the steady one dimensional heat transfer for regenerative cooling, because this heat is carried away and you can use it, heat balance across the combustion chamber wall or the we can have, that is H dot double dash, there is a total heat flux passing through this wall to the coolant is total heat flux across the wall is equal to the total heat flux getting into the coolant, and which is contributed by the H dot double dash G, that is due to the hot side convection, and H dot double dash R, that is due to radiation on the hot gas side, is equal to the same amount of heat which is coming due to convection, and the radiation will has to pass through the wall. If I consider this to be equation 1, and this is your equation 2, and this is your equation 3, and this is 4, and this is your 5, we will be using this all these equations to find out expression for H double dash in terms of temperature. By using the above equation, we can get basically H double dash and is equal to H G W A minus T W H. This is basically nothing but I am taking from equation 2, and this is your H double dash R, and I can use equation 4 for that. But now we will have to basically relate this T W A and also to T G, and then we will have to find out that, and T W H we will have to relate to the coolant, and let us do that. So, by using equation 1 and 2 along with this equation 5, we can get this as T W H. If I look at this equation itself, I can get T W H is equal to basically H double dash W, and this is your K W delta L plus T W C. So, this is the expression we can get from this equation 1, and this is nothing but that. Now, we can use this equation 3 and relate this T W C as, if you look at, this is nothing but your T W C is equal to H double dash C divided by SC plus SC, and that we can use. And keep in mind that H dot double dash W is nothing but your H dot double dash, that from here you can see this is equal to double dash by using equation 5. So, when you put all this together, I am getting an expression T W H in terms of T C, and if I know this total heat flux, all those things. Now, if I substitute this equation, let us say this is your 6 and this is your 7, by using this equation 6 and 7, I can get an expression for that. Let us do this. That is basically H dash is equal to H g T W A minus H dash. If I can take a bracket, then delta L by K W plus 1 by S C and minus T C, right, plus H double dash R. So, if I will take this term to the left hand side, I can get H double dash is into 1 over H g, because if I can divide this thing H g, 1 by H g plus delta L by K W plus S C, I will get this equal to T W A minus T C plus H double dash R divided by your H g. And if you look at, I can recast this expression as is equal to H dot double dash T W A minus T C plus H double dash R divided by H g divided by 1 by H g delta L by K W and S C. Keep in mind that this is basically talk about resistances, right. We call resistance, and this resistance is due to the hot side gas convection. This resistance is due to the heat conduction, and this is due to the coolant or cooling coolant convections 1 by S C. And this is a very important expression you should keep in mind, and you can solve the problem by using this, provided if I know the heat flux, or if I do not know the heat flux, I need to know all other parameters so that I can evaluate easily. With this, we will stop over, and in the next lecture we will be using this expression, that is your equation 8, and also see how we can apply it for practical things where one dimensionality or the area one has to consider in this analysis. Thank you very much.